Okay, so today we're going to be talking about steep turns. Um, First, what we're going to go over is we're going to talk about components of lift. So what makes an airplane turn? It is the application of bank results in the airplane moving perpendicular to its longitudinal axis, which results in a horizontal component of lift. So what exactly is that? I'm going to draw out a plane. So this is the plane. This is a plane in level plane. So at this point, you have, this is your component of lift. This is the force acting upward. And you don't have a horizontal component of lift. So you are just in straight and level flight. Now let's look at an airplane that is banked. So at this point, this is still your total lift. But now you have a horizontal component of lift and a vertical component of lift. So the vertical component of lift is always going to go straight up from the earth, and then this is going to be your horizontal component of lift. So since you have this horizontal component of lift, you now have less vertical lift. So you're going to need more back pressure to keep the plane in from losing altitude. Now, if you got a really banked plane, sorry, my plane drawing isn't the best. Now, this is your total component of lift, which always goes straight up from the aircraft. Now, your horizontal component of lift is going to be really dramatic, and you're not going to have very much vertical lift at all. So, at this point, you're going to need a lot of back pressure just to keep the airplane from losing altitude. Now, what makes the plane turn? That is going to be the ailerons. So that's one of your main control surfaces. Now the ailerons, when you bank to the left, so if this is your yoke, you're banking to the left. This is going to make your left aileron go up, right? So if this is your planes, these are your ailerons. Your left aileron is going to go up, while your right aileron is going to go down. And this is going to cause your right aileron to create more lift and therefore more drag. So this is going to cause this wing to go up because it's creating more lift, and this wing is creating less lift. So that is what makes the airplane turn. So now we're going to talk a little bit about load factors. So a load factor in aviation refers to the force experienced by an aircraft, which is measured in G's, you've probably heard that before, which indicates how much the aircraft weighs relative to the normal weight due to maneuvers like turns. So we don't normally experience that G force, that feeling of being pushed back into the plane a ton in these aircraft because you don't your normal load factor is 1 and it doesn't start rising until you get to more than 30 degrees of bank, which we don't do in our normal flight. But after 30 degrees of bank, it exponentially increases. So when we are performing steep turns, if you are a private, you're going to be at 45 degrees of bank, and for commercial, we're going to be at 50 degrees of bank, which now you have 1.5 G's of load factor, which is going to cause you to be pushed back into the plane. Yeah, so tremendous loads are imposed on the plane as the bank is increased beyond 45 degrees. So for every degree extra a bank past 45, you're going to feel those G's significantly more. So at 60, you have a load factor of 2. At 70, you have a load factor of 3, which is going to put a lot of stress on the plane. Regardless of the airspeed or type of the airplane involved, a given angle of bank in a turn during which altitude is maintained. So that's important. So if you bank the plane 60 degrees, but are then descending, you're not going to feel that load factor. So this is in this is maintaining altitude. So yeah, it's going to be the same regardless of airspeed. That's why on this chart, airspeed is not mentioned. All right. And it's also going to increase your stall speed. So that's important to note. That's why when we're going to be doing this maneuver, it's important to maintain that airspeed recommended by the manufacturer, which in our case is going to be about 100 knots for the Piper Archer. Because our maneuvering speed is between 98 and 113. So now we're going to talk about a couple aerodynamic effects that's going to affect the plane. So we'll talk about torque effect. This is going to cause a left turning tendency in the plane. This is because the internal engine parts and the propeller are revolving in one direction. And because of Newton's third law, there has to be an equal and opposite reaction. So since the engine is turning to the right, the plane is going to want to have that tendency to yaw to the left. So when you're making a left turn for a steep turn, there's going to be a tendency because of this torque effect to develop a skid, which is when the nose is yawing too far in the direction of the turn. So the nose is going to yaw too far to the left when we're in that left turn. So we'll need to apply some right rudder to maintain coordinated flight. And the opposite happens when you're in a right turn. You're going to develop what's called a slipped, which is when the nose is yawing in the opposite direction of the turn. So you're going to need to add some right rudder when you're doing a right turn as well. All right, so adverse yaw. In a turn, the downward deflected aileron produces more lift, which we just talked about, and therefore more drag. This added drag attempts to yaw the airplane's nose in the direction of the raised wing. So in this example, we're turning to the left. Let me draw this better. So our yoke going to the left. So therefore, we've got our left wing raised. This is going to, we're producing lift on our right wing. We're also creating drag, which is going to cause the nose to yaw to the right, creating a slip. So we'll just combat that by adding some rudder. The amount of rudder control required increases at low air speeds and high angles of attack with large aileron deflections. With lower air speeds, the vertical stabilizer / rudder combination becomes less effective, therefore magnifying control problems associated with adverse yaw. All right, so next we're going to talk about some overbanking tendencies. Overbanking is a result of the airplane being banked steeply enough to reach a condition of negative static stability. So now we're going to talk about static stability. So there are three types. There's positive, neutral, and negative. Now, as you can probably guess, the positive is going to be the best one, the one that we want. And the archers, fortunately, have good positive stability. So positive stability, static stability is going to be when you're in stream level flight and then you make a correction, like turning, the plane is going to go back and forth until it goes back to its original position. And neutral static stability, the plane, and you go not gonna restart this recording, but I'm messing up a little bit. So positive static stability, your plane is going to have the tendency to go back to its original position. Neutral static stability, the plane is going to not get worse, but stay with the whatever the control input was. So if you're turning to the left and then you let go of the yoke, it's going to stay in that left turn. Well, with positive stability, when you turn to the left and you let go of the yoke, it's going to return to level flight. And then negative static stability is when you turn to the left and you let go of the yoke, and it's going to increase that left turn, which is not what we want. All right. So when we're turning in a shallow turn, the airplane displays positive static stability. So this is when it initially tries to return to wings level. In a medium bank turn, the airplane will show neutral stability. The airplane will remain in that bank. And in a steep turn, the airplane demonstrates negative static stability. So the airplane will try to steepen the bank rather than remain stable. And this is when we get overbanking tendency. And since we're in a steep bank for the steep turns, this is going to be an issue. So we might actually have to add opposite aileron to maintain that bank when we're in that 45 or 50 degrees of bank. There's a limited amount of positive static stability around the longitudinal axis, so the airplane will be easy to turn to straight and level flight from shallow banks. The lateral stability about the longitudinal axis is affected by dihedral, sweep back angles, the keel effect, and weight distribution. So the dihedral is an angle in which the wings are slanted upward from the root to the tip. Dihedral involves the balance of lift created by the wing's angle attack on each side of the airplane's longitudinal axis. So this is pretty much when the raised wing is the raised wing has an increase of lift because it is having to move. It has an increased airspeed going over the wing. So this is caused by what I kind of like to think of as the track effect. So if a runner is running on a track, this is the track. A runner on the inside of the track has to go less than the runner on the outside of the track. So if they're completing it in the same amount of time, this runner is going to be going a lot faster than this runner. Same goes for the wings when we're going in a 360-degree turn. See that? So this is the plane. This wing is going to be going less of a distance than this wing. So this wing is going to be having to go faster than this wing. So in this case, we're doing a left turn, so the left wing is going to be going a much shorter distance than the right wing, and therefore the right wing is going to be having a faster airspeed. So more air is going over the wing, so it's producing more lift. And this is what the dihedral effect is. And so the increase in lift on the since the wings have a dihedral, the air strikes the low wing at a much greater angle of attack than the high wing. The increase in lift on the low wing and the decrease in lift on the high wing tends to restore the airplane to its original attitude. So pretty much the wings are wanting to get the angle of attack equal, and so this is going to give us that positive static stability where it's going to try to bring the bank back to neutral. All right, so next we're going to talk about a couple reasons why overbanking occurs. As the radius of the turn becomes smaller, a significant difference develops between the speed of the inside wing and the speed of the outside wing. So this is what we have shown here. The wing on the outside travels a longer circuit than the inside wing, yet both complete their respective circuits in the same length of time. Therefore, the wing on the outside must travel faster than the wing on the inside. As a result, it develops more lift. A slight difference between the lift on the inside and the outside wings tends to further increase the bank. As shallow bank changes to medium bank, the radius of the turn decreases, the airspeed of the wing on the outside of the turn increases in relation to the inside wing, but the force created exactly balances the force of the inherent lateral stability of the airplane so that at a given speed, no aileron pressure is required to maintain bank. But as the radius decreases further when the bank progresses from a medium to a steep bank, the lift differential overbalances the lateral stability, and the counteractive pressure on the ailerons is necessary to keep the bank from steepening the turn. So once we get to that 45, 50-degree bank, you're going to need some opposite aileron pressure to maintain that level of bank. Okay, so now we're going to talk about the procedure. So before starting the procedure, do the pre-maneuver checklist. Make sure you do your clearing turns. You want to select an altitude that's high enough so you can recover from any undesirable attitude. And just want to select an altitude that's easy to read on the altimeter. So I normally do around 3,000, 4,000 feet. Ensure the area is clear of traffic, clearing turns, establish the airspeed, the recommended airspeed by the manufacturer. So for the Piper Archers, it's going to be 98 to 113. We usually try to do around 100, and then pick a power setting that'll allow you to maintain that airspeed. I usually do around 2,150 if I can. But when you're going into the turn, you're going to want to add a little bit of power since you are losing that vertical lift. You're going to need more power and more back pressure to maintain your altitude. So entering the turn. First, you want to note your entry heading and you want to pick a visual reference point. Could be a road, a mountain, a building, something in front of you that you can visually reference. And then you also want to bug it on your heading indicator. You want to smoothly roll into the selected angle. And as you're rolling in, you'll increase a little bit of power. And then you'll also probably want to do around 2 rolls of trim so that you can keep that pitched up attitude. So here's your attitude indicator. If you're private, you're going to want to be at 45 degrees of bank. And if you are commercial, you're going to want to be at 50. Okay, so during the turn, do not focus or stare at any one object. You are going to want to find where your horizon intersects with the dashboard. So if you are rolling into a left turn, the horizon should slice the plane at about the center. And if you're on the right, it should be about 3/4. And so you're just gonna see where the plane interacts with the horizon and then reference your instruments to ensure you're keeping altitude and bank angle. And if you are, you'll check your vertical speed indicator. You want that to be at 0. If you are, then you can use this as a reference point. So in a left turn, here's your left turn visual. In your left turn, if you are pitching up too much, your spot is going to be moving to the left. So you'll see more sky and less ground. And if you're pitching down, it's going to be moving to the right, so you'll see more ground and less sky. That should make sense. And then the opposite in a right turn. So you just want to try to keep that at the same point. You can also reference your attitude indicator. I usually find around 2.5 to 5 degrees above the horizon is a good pitch when I'm referencing my attitude indicator. All right, so rolling out of the turn. You're gonna want to start rolling out of the turn when you're about 20 degrees from your initial heading. And then when you roll out, you also want to keep in mind that you did add power and trim to keep your altitude. And once you roll wings level, you're going to have an increased vertical lift. And so you are going to want to take out some power and be prepared to push forward, reduce your trim so that you can maintain that level flight. So the ACS standards, for private, roll into a coordinated 360-degree steep turn, which is with approximately 45 degrees of bank. You want to maintain the entry altitude plus or minus 100 feet, your airspeed plus or minus 10 knots, and your bank plus or minus 5 degrees. And you want to roll out on the entry heading plus or minus 10 degrees. With commercial, it's all of the same standards, except instead of a 45-degree bank, you're gonna have 50 degrees of bank, which so it's only 5 degrees, but like we said, with the load factor, that 5 degrees is going to make a big difference. 45, you got about 1.5, and 50, you got about like 1.6. So you'll definitely feel that extra G force when you're in the plane. Okay, yes. Any questions?